Digital Signal Processing Lab, experiment number 5. The aim of the experiment is to design IR filters using pole zero placement method. The filters which are designed in this experiment are first order low pass filter, first order high pass filter, second order band pass filter, and notch filter. An introduction part. Digital filters are widely designed to remove the unwanted signal components from the recombinant signals, which may be corrupted with different kinds of noises and other signals. So filter is an LTI system used to perform spectral shaping or frequency selective filtering. There are the frequency selective filters are mainly are divided into low pass filter, high pass filter, band pass filter, band stop filter, and all pass filter. So these filters can be designed by using IR and FIR approaches. In general, the filter which has to be designed has to be specified with cutoff frequency Fc, bandwidth B, center frequency F0, sampling rate Fs, and pass band attenuation, stop band attenuation, and transition width. So the pole zero placement method works on the idea of pole zero placement method is as follows. The location of poles and zeros affects the frequency response characteristic of the system. So locating poles near the points of the unit circle will emphasize the frequencies, and placing zeros near the particular frequencies will attenuate the magnitude response of that particular frequencies. So the constraints of this pole zero placement method is all poles should be placed inside the unit circle for ensuring that the filter is stable. That is, the filter response, the output y of n should not become unstable for any type of input. And also the real filter coefficients. All complex poles and zeros must occur in the complex conjugate pairs in order for the filter coefficients to be real. The practical limitation of this pole zero placement method is when the band pass and band stop filters have a very narrow bandwidth requirement, only under this type of specifications the pole zero placement method has good performance. And the low pass and high pass filters have either very low cutoff frequencies close to the DC, or for the high pass filter the cutoff frequency is close to Fs by 2, which is the folding frequency. Now the design of IR filters using pole zero placement method. The experiment question. In this experiment, we design low pass, high pass, band pass, and band stop filters using the pole zero placement method. For each of the filter specifications, we need to find a transfer function, sketch the magnitude and phase responses, and pole zero plot, obtain the difference equation for each of the filtering system, and obtain the output of each of the IR and IR filter systems for the ECG and PPG signals which are sampled at 360 Hz. And write your observations based on outputs and the magnitude responses. So the specifications for first order low pass filter is as follows. Fs is equal to 360, 3 dB cutoff frequency, Fc is 40, and 0 gain rate 180 Hz. So 180 Hz is Fs by 2, Fc is Fs by 9. For any low pass filter, first h of z is equal to k into z plus 1 by z minus alpha, where k is equal to 1 minus alpha by 2, ensuring that h of j omega is equal to 1 and omega is equal to 0. Fc is less than Fs by 4. If for the case for the question given, since Fc is equal to Fs by 9, alpha is equal to 1 minus 2 into Fc by Fs into pi, 0.3019, k is equal to 1 minus alpha by 2. So the transfer function obtained is 0.3419 into z plus 1 by z minus 0.3019. So the difference equation obtained by applying the inverse Z transform gives y of n is equal to 0.3019 into y of n minus 1 plus 0.3419 into x of n plus 0.3419 into x of n minus 1. The obtained magnitude response for the first order low pass filter, which has the maximum gain at 0 and at 180 at 0 gain at 180 Hz. This is a pole zero plot. Since it has 0 gain at 180 Hz. 180 Hz is Fs by 2. So this is the point Fs by 2. This is the Matlab code for obtaining the frequency response using freqz command, which has arguments of the arguments AK and BK, and pole zero plot is obtained with TF and PZ map. This is the code for simulating a real-time PPG signal. Given a PPG signal, we derive a length y of n signal from x of n of length n. Given an input signal of length n, we obtain y of length n by using this simple first order low pass filter. The plots obtained is as follows. Clearly, we can see that the number of spikes are reduced and the y of n is smooth. The high pass filter, the specifications of high pass filter are fs is equal to 360, 3 dB cutoff frequency is 1 Hz and 0 gain at 0 Hz. And the transfer function for high pass filter using pole zero placement method is k into z minus 1 by z minus alpha, where alpha is equal to 1 minus 2 into fc by fs into pi, k is equal to 1 plus alpha by 2. So which gives h of z is equal to 0.9913 into z minus 1 by z minus 0.9825. And obtaining the differential equation, y of n is equal to 0.9825 into y of n minus 1 plus 0.9913 into x of n minus 0.9913 into x of n minus 2. This is the magnitude response for the high pass filter with cutoff frequency of 1 Hz. So at 1 Hz value is 0.7023, which follows the specific requirements, and the pole zero map. Since the cutoff frequency is close to 0, it must be placed close to 0. And this is the code for simulating a real-time PPG signal for a simple first order high pass filter. As we can see, the faster time variations are emphasized in the y of n. The requirements for band pass and band stop filter are provided here. This is for band pass filter, which has sampling frequency f is equal to 360 and 3 dB bandwidth is equal to 14 Hz, and narrow pass band, which is f0 is equal to 13 Hz, and 0 gain at 0 and 180 Hz. So the using pole zero placement method, h of z is equal to k into z minus 1 whole square by z minus 1 into z plus 1 by z square minus 2 rz cos theta plus r square, where r is equal to 1 minus 3 dB bandwidth by fs into pi. Theta is equal to f0 by fs into 2 pi. So this gives k to ensure that h of j omega is magnitude of mod of h of j omega is equal to 1 at omega is equal to 0. K is equal to 1 minus r into under root 1 minus 2r cos theta plus r square by 2 into mod sin theta. For the given specifications fs 360, we get h of z is equal to 0.1 into z square minus 1 by z square minus 1.7 into z plus 0.77, which gives the differential equation y of n is equal to 1.7 into y of n minus 1 minus y of n minus 2 into 0.77 plus 0.11 x of n minus 0.11 x of n minus 2. This is this code for obtaining the magnitude response and pole zero plot using PZ map and TF and flip set. This is the obtained magnitude response for band pass filter, which has a centered frequency of 13 Hz, 14 Hz. This is a pole zero plot for the band pass filter. As you can see, the poles are mirrored with respect to x-axis, which means they are conjugate pairs to give real filter coefficients. And this is the code for simulating the real-time PPG signal using manipulating the array of x of n. The obtained graph for the band pass filter. The notch filter has specifications f is equal to 360, 3 dB bandwidth is equal to 4 Hz, and narrow passband centered at f0 is equal to 50 Hz. The transfer function using pole zero displacement method is k into z square minus 2z cos theta plus 1 by z square minus 2 rz cos theta plus r square, where k is equal to 1 minus 2r cos theta plus r square by 2 minus 2 cos theta. Given f is equal to 360, h of z we get 0.967 into z square minus 1.286 into z plus 1 by z square minus 1.241 z plus 0.931, and we get differential equation as y of n is equal to 1.241 into y of n minus 1 plus 0.931 into y of n minus 2 plus 0.96 into x of n minus 1.244 into x of n minus 1 plus 0.967 into x of n minus 2. This is the magnitude response obtained for a notch filter. This is the pole zero plot. Since the filter coefficients has to be real, the poles and zeros are mirror image with respect to the x-axis. This is the code to simulate a real-time PPG signal. The obtained response is as follows.